Hello everyone, Stefan here from Civils AI. And today I want to talk to you about construction AI agents. I want to talk to you about construction AI, how we're using these AI agents in particular, and how you can build your own. So here is a little bit about me. So I was a civil engineer before, working on tunneling projects, doing lots of geotech design, tunnel lining design, settlement calculations, all of this stuff in the UK. And then I moved out to Singapore. And I've been doing Civils AI for about 2 years now. So self-taught web developer. So I coded a few different projects before starting Civils AI. And yeah, today I'm going to be talking more on the AI side of things. So this is the topics of this presentation. Feel free to skip ahead to some section that you think is more interesting. But I wanted to do some high-level intro into the topic of AI and try to explain it in simple terms that engineers and architects and BIM folks can all understand. Then I want to talk more specifically about this concept of AI agents, which I think is really powerful and kind of the future, and how we basically how you can build your own. So I'll give you some starting guidelines on how we've built them and how you can start doing your own, as long as you promise not to try to replicate Civils AI with this knowledge. And then I want to say how we're using them, so what our approach is, and maybe say a little bit about our future plans. So yeah, let's get started. So this is the simplest possible explanation of AI and machine learning that I could put together, and this is the way that I think I try to explain it when people ask. So the idea is that you have input data, which you know, so it could be some real world data points that you've observed, and then you have some known output, which is something you think this data may be linked to, which is also data you've recorded. So this could be like various different types of data, but let me just give some examples. So perhaps you have data relating to number of times that you've seen people not wearing construction PPE, like safety equipment on the project, and the days that this happened. And then your output data is like the days on which accidents happened where someone got hurt. And so you know that these are probably like linked in some way, that, you know, if people aren't wearing the safety equipment, they're more likely to get serious injuries, but you don't know the relationship or the function relating these two. So it's not the nicest example for me to use, just came to me. But this is some function which can be approximated, which links some input data with some output data. And all it is really is maths. So essentially it boils down to some mathematical approach. And I'll go into how you can do this some more, but essentially it's just function approximation. Quick history of AI. So when people normally think about this subject, they think that it's this like emerging technology and it's the future, and you know, it's the most cutting edge thing that we're doing as like the human race. But actually it's much older than most people consider. So yeah, essentially AI algorithms are just mathematical constructs, and these have been worked on since the 1800s. So before we even had our modern computers, there were these famous mathematicians who were actually creating these foundational concepts, in particular, you know, with neural networks, which I'll talk a bit more about. But these were being researched in the 1800s. And like moving on from that, there was some theory that actually these neural networks that we use today that are so popular, they weren't actually going to be the future. People thought that other methods, like known as simulation and heuristics, that they were the future. So simulation, you may have heard of Monte Carlo simulations, things like this. There's other types that fit into these two, but like Monte Carlo, you may have heard of. People thought that some of these approaches would be the most powerful, and basically these neural networks were kind of left to one side for a while. They weren't that popular. However, there were some breakthroughs that happened. Backpropagation, you may have heard of. These two are basically some architectures for the neural networks. And then we come through to today, where it's quite widely agreed that these neural networks are really powerful and that they are potentially going to solve some of like our biggest challenges. And yeah, are very popular now. So it's kind of like history and how things have changed in this school of thought. But why is AI becoming increasingly powerful? Why is it we're having these breakthroughs happen and suddenly like neural networks are popular again? So it's all to do with cost of compute. So there's a theory that cost of compute is in the long run coming down, trending to zero. And there's essentially GPUs have like made a lot of this quite possible. So GPUs, there's a reason why NVIDIA has become one of the most valuable companies in the world, because they produce these GPUs. And GPUs are essentially graphics cards that used to be, still are used for like games rendering on computers, but they found that they're really good for also training AI models. They make it much more efficient, cheaper, and more powerful, so they can be used to train AI models more effectively. And basically, the GPUs are getting increasingly powerful, and it's meant that model training is easier. There's also new libraries that have been released, like TensorFlow, PyTorch, and these kinds of developer tools that are making it easier for people to build these AI models. The chart on the right is called Moore's Law, and this is some theory that every 2 years, the number of transistors on a microchip doubles. The x-axis here is the years, so starting in 1970 through to like today. You can't see it because of my face, but then the theory is, so each point on this chart is a different microchip that was released. And this is a log chart. The y-axis is logarithm, so this is actually an exponential increase in the number of transistors on a microchip. So this is like underpinning all these breakthroughs. Like the computing power we have today is able to prove many of these mathematical models that have been worked on for 200 years. And just now we're able to build this into products, which is a very cool time. We're lucky to be living in this era. And so this slide, I want to try and clarify some of these common misconceptions and definitions. So when we talk about data science, so data science like AI, ML, you hear people use these interchangeably, and sometimes I feel that people don't even know like what is what. So basically, data science is this overarching subject matter which includes all of this, like AI, machine learning. So if you wanted to study this subject, you might want to study data science at university, and that will capture all these things. So data science is everything. Then AI is basically just, the definition is it's a non-natural construct which can take a decision without human intervention. So the key here thing is it's not biological, and that we don't necessarily need to be kept in the loop, like making decisions and stepping in to guide the software. It can run autonomously. A common misconception is that like machine learning and AI is the same thing, but actually so machine learning is one approach to creating these AI algorithms. So this function approximation, machine learning is one approach to creating that function approximation, but there are other alternatives to creating these functions, things like Bayesian networks. Other methods can be used, but machine learning is probably the most popular one that people are aware of the most. Artificial neural networks are generic function approximators. So this is some way of estimating that function. Is one technology that can be used to do that. And basically, deep learning is a neural network that has more than 2 layers. So it is a more advanced or more powerful version of just a neural network. But deep learning is just 2 layers to this thing. So that's very high level, very quick, but this is some definitions. As engineers, so this is like trying to link into engineering and construction a little bit. So most of us as engineers are already using these foundations of machine learning in our engineering, and most of us aren't really aware of it. So when we say, oh yeah, like we're not using AI in this company, actually, people who are skeptical about it, they don't realize it, but they're actually already using a lot of this stuff anyway. So any empirical calculations you're doing on construction projects or in design are some form, like in its principle, of machine learning, which has, so here's a case of some geotechnical calculation, which is stand-up time. So stand-up time for a cavern, a mined tunnel or a cavern in rock, and some parameters or data relating to that cavern that can be measured on the site, like the span or some cracks rating, basically. And each point here is a different project from the past. So this is in a report or a document, and this author has basically created their prediction or their correlation between this data that you can follow in order to make some calculation. And so this is actually a machine learning problem. So if you feed this data, do some of this function approximation that I was explaining, you can generate some of your own correlation between this data. So this is an AI problem. And the only difference here is, I believe, when this was written, this was done by the author with perhaps some mathematical model themselves, but this could equally be done by machine learning like application. So yeah, we're all using it already, basically. So different technologies can be used for the function approximation part. So here, I'm just going to talk about some of those very quickly to explain what they are. So when you hear the terms come up, you sort of know what they mean. And what you have is classical machine learning. So it's changing very quickly, but up until like last year or 2022, actually many applications that said they're using some AI are actually using some classical machine learning approach. So they're using something like linearly square regression, like lines of best fit, essentially, decision trees, things like this, to add in some element of AI and some prediction. So you can imagine these could be actually really advanced, predicting like financial crime, like lots of things in financial markets use something like this as well. So many AI apps would use like this classical machine learning approach. But you have, like, in terms of neural networks, you have like deep neural networks can do text to speech. Recurrent neural networks also can do this. Won't go into it in more detail than that. Convolutional neural networks are like vision intelligence or image recognition. So you use these convolutional neural networks for self-driving, some of these problems, solving vision, like replicating the features that we use our eyes for. Transformer models, this is what powers ChatGPT. These are used in large language models. I'll talk a little bit more about this later in the presentation. Graphical neural networks, autoencoders, these are for recommendation engines, and these can map relationships between different objects. So some objects can be very complicated. You can have many parameters and ways things are associated when you think about them. So these can map relationships and similarity and closeness between different objects. These can be used a lot in like Spotify, Netflix, things like that, where if you listen to some artist, it will recommend another similar artist. So these are all, these use these types of technologies. Generative models, these are used in like stable diffusion, like image generation, where it creates some like brand new image that's never been seen before. So these are all technologies that can be used as part of that function approximation. And they're better suited to different things. If you try to use one of these in a different category, it will like not perform as well, essentially. So now onto the topic of AI agents. So before we really dive into that in some detail, it's important to say what are transformer models some more. So all of the AI agents I'll talk about in this presentation will be some form of transformer model, actually. But transformer models are not just large language models. It's like the most popular right now, and like lots of people, when they think of transformer models, they'll think of large language models. But there are other types. There are some other types of transformer model that have been released, like NASA released one for GIS data. There's a few others. So, and the way these work is basically, or the way you build them, is they map like sequential data. So when I talk about sequential data, and a good way to think about it is like a sentence is sequential data. This is why large language models have become so popular. In essence, when I'm speaking, each word that I say is linked to the words previous. So you build it up in a sequence, sequential. So these transformer models are very good at mapping the sequence of the data and predicting what is likely to be next in the sequence. When you talk about these things, you don't talk about words necessarily, but you also use the word tokens. So it's very good at predicting the next token in a sequence. But this could be anything. You could also do one with like maybe numbers, where it's like just counting 1, 2, 3, 4, 5, 6. This could be sequential data, which can be used for a transformer model, although it probably won't be very useful in that case that I just said. So the way this kind of works is, let's say you're feeding a sentence into a large language model, the sky is, then this thing's been trained on like many millions, billions of sentences that it understands. And so it has probabilities of what the next token is most likely to be. And here's like what's happening in that as the outcome of this like neural network here is what you're seeing is like probability. So likelihood of blue, likelihood of clear, usually the, and so it's predicting that blue is the most likely next token. So your output, which is returned to you, is the sky is blue. This is the main thing that's happening here. And the idea is that they can understand meaning. So if you train enough sentences in here, it doesn't just predict the next sentence, but it kind of understands the meaning. And people start to say that they then demonstrate intelligence and they can pass our exams, and like what's to separate our intelligence from the intelligence of a large language model. So this is where when you get enough sentences in here, in the training at least, it starts to appear as though it understands meaning. And so these AI agents are basically built by abstracting upon these foundational models, so these transformer models. So you could have, let's say, the idea of this is that by using AI agents, the performance of your transformer model, your large language model, can be improved by connecting these different transformer models in a workflow. So you can have different configurations. This is not the simplest configuration by any means, but you can interact with one transformer model that has other transformer models that it speaks to before returning the answer or the result back to you. So the idea is you perhaps set some objective, some task, you pass this task to one of the AI agents, and then they work together to produce a result that is better than you working with a single AI agent alone or a single transformer model. So I'll move on to the next slide with an example. So I would say this example is the simplest of the AI agent configurations. So in this example, you have what is known as a user proxy agent. So this user proxy agent has two functions. So you interact with this user proxy agent as the user. So I'm the user, Steban. I'm interacting with this guy. And this guy also, his responsibility, other than to speak with me, is also, in this case, to execute some Python scripts. So this agent has the permission to also write out and execute Python scripts within some virtual environment, let's say. You then have this assistant agent. So the way to think of this assistant agent is perhaps just like the way in which you use perhaps ChatGPT or some large language model already. This user proxy agent mimics the user and interacts with this large language model in the way that you would as the actual user. So let's have a look at how this would play out. So this is some case from some documents online. It's not original, not related to construction, but just helps you to understand. So if you follow this sequence, so me as the user myself, I get this started by speaking with the user proxy agent. And I say, plot me a chart of some stock prices and how they've changed over the year. The assistant agent then receives this communication and provides some code back. Execute this following code, blah, 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 write something back. This user proxy agent then has the power to write Python, execute Python. So it tries to do that, and it comes back saying, okay, within this virtual environment that I've created, I don't have this library I need, Y-Finance. It's not installed. So the assistant agent comes back and says, okay, just install this first, and then execute the code. So the user proxy agent receives this, doesn't need any human intervention so far. This is all autonomous, solving the problem itself. It begins installing this library. Once this library is installed, it is then able to generate the chart. The user then steps in and says, actually, no, I don't want this data presented like this. I want it presented differently. And so the assistant agent then receives that instruction, creates new code, and the user proxy agent generates this chart again. So the idea here, this is very simple and perhaps not the overall best demonstration of the power, but to explain the concept that what you're doing here is two of the AI agents are chatting amongst themselves in order to remove some step that the user needs to perform some instruction. They're working autonomously to improve the output of the results. So this is a simple case, but demonstrating this crazy power that they can actually have in working together. There are multiple agent configurations, so I won't touch on these in this presentation, but there's multiple different configurations which can be used for, some are better suited to different tasks. So in the docs, in the way that I'll show you how to build these things, there'll actually be different cases where you can experiment with these. So multiple agent configurations. Okay, so the real power of the AI agents, and this is the thing that I really want to emphasize in this, is that they can solve complex problems without this need for traditional AI development approach, which can be very expensive and time-consuming. So let me give you a typical AI solvable problem. So let's say you're working on a construction project as some safety manager, and you're very busy, you're extremely busy, and you want some help in just knowing if, when you're not on the site, people aren't wearing their helmets, and you have no alternative. So you need some software for it because you have no one there who can help you. So let's say you have some photos or some video stream that you can receive, and you want to just detect if people aren't wearing helmets when you're not there. So what you can do, this is an AI problem. So the traditional way of building this application would be you have to basically get many, many photos. You have to get tens of thousands of photos of people wearing helmets, different colors of helmets, different angles, different lighting conditions, every single case. You want to try and map it. You want to try and get a photo of that case. So you have every possibility covered. And then you may have tens of thousands of photos. You could have even more than that. And you then want to label these. So this is a human, there's not really much automation that you can do to actually label these. This is a human task. Someone has to sit there and draw bounding boxes around each person who's not wearing a helmet, and perhaps even each person who is wearing a helmet in the photos. So you start to get a kind of archive or some reference data. This can be expensive and time consuming. It could be 6 months or a year of labeling data. So generally, this shouldn't be done unless it's a really costly problem. Because you can get really caught up in this and tied up. Then you use some library this is a Python one, convolutional neural network called YOLO, you only look once. It's quite a popular one. Then you take all this label data and you train some convolutional neural network on this problem. You then have to probably do this for a few cycles and you have to be concerned about things like overfitting and all these modeling complications. and go through some cycles of this. And then you have to then put this into production in some way in which you can actually interact with it, because obviously you need some way of uploading images. All of this it's tricky, and not many people without training can do this. So, and then eventually you get your application. So this is tricky to do. Using AI agents is very different, extremely different. So essentially, the way you'd approach this from the AI agent perspective is you have your image, like let's say people who are wearing helmets, someone who isn't, and you have an AI agent workflow made up of multimodal conversable agent, code agent, command agent. Essentially, you then give instructions just to this AI agent, saying, provide, with this guy, find the coordinates of people who aren't wearing a helmet, x min, y min, x max, y max. So you have a rectangle of the coordinates. Then pass this to the code agent, who will modify your original image to include the bounding box of this person not wearing the helmet. Then pass it to the command agent, who's going to save this image somewhere and store it for you. The idea here is that this image can be broken down into binary data, which a large language model can then understand. So essentially, your JPEG PNG file is a series of a string of data, which can be read by a large language model. So in essence, this is being passed to this guy, who's then giving the coordinates, then written into the image, then saved. So this is very flexible. All you do is you change the instructions to the AI agent. If you want a different color here, or you want a different, okay, that's not the best example. Let's say you want to switch and change it to people not wearing gloves as well. With this approach, you'd have to get lots of pictures of people wearing gloves, wearing helmets and wearing gloves, people wearing neither, and you'd have to relabel all that and do this all again. With this approach, you actually just change the prompt. So it's really flexible, saves you years of training time, potentially. So how can you build your own agents? So the best place to start is LangChain, AutoGen. These are two open source libraries. You'll find them on GitHub. LangChain, the link's here. And essentially, to get started, it's just a couple of lines of code. It's just 10 lines of code. Typically, some AI applications, you don't see that many lines of real code. That's it to get started. AutoGen, this is a Microsoft open source project. Also really useful. Lots of people, we use LangChain, but other people have told me that AutoGen's also really good, and I've looked at it myself, and it looks powerful. So this is, again, just a few lines of code. So you've got two here. Then here's some project ideas with AI agents. So if you want to build your own, here's an idea to get started. These AI agents can be trained on APIs. So you can tell, let's say LangChain in this case, a bunch of APIs that you have for some software or some tool that you're using. You tell it the parameters that the API takes, what you're expecting back, the output and what data format you're expecting, and some description of the different APIs. You pass that into your AI agent, and then you can just query with natural language and retrieve results. So in this case, Plaxis, you might retrieve back bending moment for the tunnel lining results. That data, you can just say, get me the bending moment results. So yeah, making APIs super easy to interact with. And yeah, it's really easy to get started with this one. This is from the LangChain docs. It's actually for weather API, but essentially this is all it is to create that, just a few lines of code and referencing to where the API documentation is. You then have RAG, so retrieval augmented generation. So we use a bit of this with Civil's AI. And the idea here is you create an AI agent which understands some documents, some private information, let's say. And here you can take these documents, sync them with LangChain, an AI agent, and then query these documents back. And again, this is very easy to get started on. It actually becomes much more complicated than this when you actually dive into it more. But this is in essence how to get started with RAG. And have a go with this. It all runs on your local computer, so long as you don't have many files here. And so again, this is however many lines of code you need to really get started. LangChain's super accessible. Okay, so project idea 3 is basically searching big data sources for information. So let's say you have a huge IFC file on your project that's hundreds of thousands of words or lines, and you want to be able to interact with that. You want to modify data or read data from it and interact with it. So with large language models, they have a context length usually where you can't put over a certain number of words into the prompt. But what you can do with some AI agents currently is you can actually provide a data source. So you can provide your IFC file with a data source for this agent, and then be able to query this in its entirety rather than just a chunk that you can feed in. So this is a way of mapping in a big data source. So third idea. Now, how are we using AI agents at Civils AI? So the problem that we are trying to solve with the AI agents is the big issue of rework on construction projects. So what you have on many projects is you have like thousands of documents that are being worked on by architects, structural engineers, mechanical engineers, contractors. Everyone's like constantly making changes. And the project manager's job is to understand the latest information, coordinate it with all the people, the different disciplines, make sure that people aren't using the old data. Otherwise you get rework issues, and people are out of sync. So you have this issue of coordination and keeping everyone working with the latest information. So what we're trying to do with Civils AI is solve this rework issue. This is our mission. So the current product, what we've built it into is we use some AI agents to understand all the project documents. So we can do this straight from the API. So from Autodesk Construction Cloud, from Procore, from Bentley Connect, SharePoint, any of these have APIs. So read the documents and analyze them. So we read all the construction text, tables, all of this data. From this point, you can then search for the latest construction information. You can type in what's the latest concrete strength test results for the columns on some particular section, and it's going to read through all the tables, read through all the text, and find that table and answer your question, providing some reference and citation. We also, while we're analyzing the files, we organize them, categorize them, so all the information is neat and organized by disciplines. So we take it from some messy document management system, perhaps, and or even folders, and put it into a really clean, organized format. In terms of the search feature right now, this is a bit how it looks. I won't go into it too much, but you essentially can ask questions, get some instant answers back with citations saying where the information came from. You can also click reveal all references, and this is like a Control F feature where if you click this, you're going to find all the mentions of this specific key term, like building height. And if you click these links, it's going to show you exactly where it is in the documents. It's going to open up your file and show you. So the way this works, you basically use vector databases and understand the text, tables, and convert it into a vector database. We can do IFC files. Drawings are still as in traditional PDF. CAD files are still work in progress. And then basically use some large language model to interact with this data. In terms of data privacy side, right now when we get started, we do this on our cloud. So we suggest not starting with overly sensitive data or some NDA data, but actually if you're enjoying finding benefit in the solution, we can actually just host this on your own company cloud, so you're in control of all the data. So we've done this with a few of the clients for sensitivity reasons. Then we've been working with different consultants, contractors, and basically helping with different things. And that's about everything I wanted to talk about. So our vision is to make the world's construction projects safer, more cost efficient, and sustainable using generative AI. Thank you very much for listening, and do get in touch if you want to learn some more about our work. Thank you very much. Bye-bye.